Dear student, let us begin lectures on machine design part 1. This is lecture number 14 and the topic is design of fasteners. This is the continuing part of the lectures on the same topic. Now in the last class, that is in lecture number 13, we studied how to design a fastener, that is a mechanical joint. Now in that class we have designed what is known as the knuckle joint, that is the fastener is a pin type joint. Now we are going to study different kinds of joint today. Mostly we are going to concentrate on a type of joint which uses a mechanical element which is known as cotter. So let us go to the topic proper and let us see what are the different types of cotter joints. Now what you see here is one kind of cotter joint, and here you see this part. There are two parts which are to be joined by means of a cotter. Now this is known as a cotter. A cotter is like a pin, but it has square cross sections. If you want to draw the cotter, then it looks something like this. So this is a cotter in three-dimensional figure. Now you see there is a taper here. So there is an angle, taper angle theta. This taper angle is usually very small, but it provides adequate binding force. So this is a cotter joint. Now this kind of cotter joint is known as a socket and spigot type cotter joint. So this is a socket and spigot type cotter joint. So the spigot is here. This part is a spigot, this one. Now this is in the form of a rod, and the other part which is hatched over here, so this part is known as a socket. As the name implies, it has a hole inside through which this spigot enters, and these two parts are joined together by means of this cotter. So the purpose of this joint is to to bind these two elements when they are under tensions, as you see here, but it can also sustain some compressive force because of this collar, a little protrusion, as you can see here. Now if you think of this diameter is taken to be d, where this is different, d3, which is greater than d. So therefore this collar, it provides compressive force when compressive stress when a compressive force is given. So instead of P, if we can give P over here, then it develops compression. So this joint can withstand both tension and compressions. Here what you see here, a clearance is made between these two parts, that is the socket part and the cotter, of about 2 to 3 millimeter. So this clearance is required to insert this cotter. Now we are going to design this, going to see how to use the failure theories for this kind of joints in a great details, but for this time being let us see different other kinds of cotter joints. Now this was the very simple joint which is known as a sleeve type cotter joint. So this is known as sleeve and cotter joint. What you see here, there are two rods which is here, one such is up to this part and another one is here. So they are connected together. Now how the connection is made? Now it is made with the help of a sleeve. Now this part is known as sleeve, as it is mentioned over here. This is the sleeve. So this is just like a hollow pipe. Now these two pipes are put inside this hollow pipe, and then the hollow pipe and the solid pipe, they are connected together by means of two quarters. Now here the normal distance between them is, if the d is the diameter of each of this pipe connected together, then normally 4.5 d is this length which goes in, or which is the joint length for each pipe. So the total distance is 9 times d. Now this is rough, and this is normal, the standard distance used. Now of course the other dimensions are given here, but these are very important while designing. But now we are not going to design this one, but different other joints. But what you see here, there are two quarters, and the for the sleeve and quarter type joint, the tapers are in the taper sides are facing each other. This is very important, and this is normally done so. So this is what you see here is a sleeve and quarter joint. This is also very important kind of joint. Now let us go to the next type, which is a gib. This is known as gib and quarter joint. Now this type of joint is normally used to connect the large end of the connecting rod. Now there is a strap end. So this, the outer periphery, this one is known as strap. This is the strap, and when you have this strap, then without this part which is known as gib. Now gib, without this part, the strap tries to open up. That is, if we have a strip, if you have a strap like that, so if we have only a strap and a quarter, so because of the friction force here, the friction developed over this surface, the strap tries to open up. So this part, without this gib, it opens up. Now in order to resist that, we provide another element which is known as gib. Now gib is nothing but a mild steel piece which has the same thickness as the quarter, but which has this kind of shape. Now what is the purpose of this shape? You can see this strap which normally tries to open up because of the friction force between the strap surface and the quarter surface. This gib, because of its integrated geometry, as you see, this part has some protrusion, that is, when the strap tries to open up, this part withholds that. So in that case, the strap is secured against the connections. So this is the purpose of the gib. Now there are different kinds of arrangements of gib. This is what you see at double gib, that is, two gibs are put here, and gib has also the taper, and the taper angle is same as that of the quarter. As you see here, there is no gap between the gib over here, and there is no gap. So this is the gib surface and this is the quarter surface. So there is no gap between the gib and the quarter. So gib is a very useful member in that kind of joint. So normally these are the different kinds of joints which uses quarter. Now we are going to study in some more details how to design such a joint using quarter. So let us go to design of quarter joint. First of all, let me draw a quarter joint. Here we are going to use the socket and spigot type joint. Now the spigot this is the socket. It has hole inside, and we have another component which is known as spigot. This part is spigot. And through it we insert what is known as the cotter. So, this is the cotter inserted. Now, when we apply a force P, tensile force, then different parts are subjected to different kinds of stresses. So, let us analyze one by one. First, let us take the case of spigot. So, this part is known as spigot, and this is socket. So, first of all, this spigot, it will try to tear up. Now, the most important most important part is this part that is the rod end. Now, as you see, the tensile stress developed here is nothing but sigma developed when you take a cut over this surface. Then we get the tensile force, tensile stress is P divided by area of cross sections pi by 4 d square. Now, this must be less than sigma allowable. If I can remind you that sigma allowable is nothing but sigma ultimate, the ultimate stress divided by the factor of safety. Now, sigma from this data we can calculate what is that d. So, given a force P, we first calculate the diameter. Now, if you remember the diagram, then all the data, all the other dimensions are given in terms of this d, the diameter of this rod. So, this is very important, and we will have to find it out quite carefully. Then, what are the other modes of failure? You see, this, now let us consider the spigot. Now, you see the critical section of the spigot is somewhere here. If you look from the top, the spigot looks like and the cotter is inserted over here. This is the cotter insertion point. So, therefore, and these are circular cross sections. So, therefore, the critical cross section will be somewhere here. And if you find out if you draw the cross section, then it looks like here, through which the cotter passes. So, this is the critical cross section of the spigot. Now, the tensile stress developed here will be equal to sigma is equal to the normal force is P divided by the total area, which is equal to pi by 4. Now, if this diameter is d1, if this d1, d1 square minus, and the thickness is, let us say, t, then d1 times t. So, this is the total area over which P acts. So, this is the stress, and this must be less than equal to sigma allowable. So, from this data we can find out d1. The d1 value when found out, then we can go for some other calculations. Now, the cutter will rest against this part. So, therefore, there is a chance that a crushing may take place between this pivot and the and the cutter. So, let us calculate that. So, this is the spigot, and that is the surface over which the cutter rests. So, therefore, the crushing stress, that is compressive stress developed, is equal to P divided by pi, or this total area, which is equal to d1 times t, and that must be less than SC, that is the compressive strength. If that exceeds, then of course the failure will take place and the surface will be damaged over here. So, damaging takes place if the sigma c becomes larger than SC. So, in that way we can check for the crushing stress. We have already selected T and determined D1. With this we check. Now, failure theories are used not only to determine the design parameters, that is to make the dimensions, but also to check against failure. So, here is the case where we have already determined the proper dimensions, and now we have checked against failure, and the failure is due to the compressive stress. What are the other modes of failure? You see that once the cutter is once we give a force P, then the cutter may be sheared away. How does it take place? Let us see. What we see here, again this is the spigot and this is the cutter. Now, if the force is given here, then a large force is developed, large stress is developed, and that stress may be such that this part gets torn away. That is, it may fail against this direction. Now, what is the area of cross section? As you see, the total area of cross section is now this distance times this one. So, this is the total area of cross sections. We have to find out that total area, and this is nothing but so it may tear away because of the shear stress will develop here on this surface, and the total shear stress is d times d1 times this distance. If you call this distance c, the d1 times c will be the surface on which the shear stress develop, and this is twice of that because there are two surfaces, and this is the total area. So, P divided by that will give you the shear stress, and that must be less than tau allowable. If that is not satisfied, then this entire part will be sheared away, and we have to resist that. So, from these equations we can determine this value of C. Now, this is how the this spigot can fail when subjected to tension. Now, if it is subjected to compressions, then there may be other ways of failure. Let us see one. Now, when there is compressions, you can see that there will be a stress developed on this surface. Here the stresses will be developed because there is a collar here, protrusion. So, when we give a compressive force, now we are of course giving compressive force. P and P over here. So, now if you draw the cross section over here, then what you see, this spigot, this diameter and the inner diameter. So, this part is subjected to compressive stress. Now, what is that value of compressive stress? Sigma C is nothing but P divided by, if the two diameters are, let us say here D1, this one was D1, and if we call this to be D2, then pi by 4 D2 square minus D1 square. This is the compressive stress developed, and that must be less than SC, the strength against compressions. So, this is to be satisfied. From this we can design the value of D2. What is the other mode of failure? As you can see, it can shear away even about this part. So, with this it can be sheared. Now, let us see that what is the shearing, what is the shear stress developed. As you can see, the total surface over which the shear occurs, now this is the collar, and the shear takes place over here. If the force is too large, we have P over here. So, the shear occurs over here. So, what is the total surface? Now, this is cylindrical. So, therefore, the total surface area is nothing but pi d, and this diameter, which is equal to d pi d times this thickness T1. This is the total surface, and when this is when P is divided by that quantity, we get the total shearing stress, and this must be less than T tau allowable. So, tau is equal to there. If this is not satisfied, then this part will be broken, and this only occurs when there is compressive force. If instead of compressive force we have a tensile force, then of course here no stress is developed, it only just touches, or there may be contact loss. But whenever we have a compressive stress, there will be, these two parts will be in contact, and in that case we can have compressive stress. So, this is how a spigot may fail under various circumstances. The first kind, as I said, this is tearing, the second is crushing against cotter, the third one is shearing of the spigot because of the stress developed between cotter and contact stress developed between cotter and the spigot, and in the case when the compressive stress is given, compressive force is given, then there are two other kinds of failure. One is the crushing of the spigot collar against the socket collar and the shear of spigot collar. So, this is how a spigot will normally fail. Now, let us look at the situations of socket. The analysis is very similar to that of the spigot. Now, the socket, if we draw the socket part, so this is the socket, and we have a cotter passing through here. Now, again it is subjected to tensile force, as you can see here. So, this is subjected to tensile force. So, when this is subjected to tensile force, then of course, the socket can tear, and the critical cross section will be somewhere here, as you can guess, and you have seen for the spigot. If you draw the cross section, this is hollow, remember, and the cotter passes. So, this part is subjected to tension, and therefore, sigma is equal to P divided by the total area. The area is, if this is D1, inner diameter is D1 and the outer diameter, let us say D3, then pi by 4 D3 square minus D1 square minus this much, which is equal to D3 minus D1 times T into D3 minus D1. So, this is the sigma, and this must be less than, so this sigma must be less than sigma allowable. This condition has to be satisfied. Now, with this we can find out the value of D3. This is failure against tension, that is tensile failure. We have other kinds of failure just like spigot. Let me describe. The spigot or the socket will fail against crushing. So, if we find out, there will be the crushing force developed, that is the compressive stress will be developed on this surface. So, if you find out, if you draw the cross section area of this surface, what you find out that this part is subjected to a contact force P. So, therefore, the contact stress developed is sigma C will be equal to P divided by this total area which is equal to T times D3 minus D1. So, this is T times D3 minus D1. So, this is sigma c, and that must be less than SC, the compressive stress. Otherwise, this surface will be ruptured or it will be crashed, and that is to say this surface will be damaged and the joint may fail. The other kind of failure is again shearing of the spigot of the socket collar, that is, this part is known as the socket collar, this one, and if the distance is taken to be A, then the total surface over which the shear stress developed is nothing but, let us find out the shear stress. Remember, we are dealing with the shear stress on that surface, that is, this is the spigot collar, and this entire surface so this part is subjected to the shear stress, and the shear stress is nothing but tau will be equal to P divided by this total area, which is equal to this distance A times this part. That is, if you draw the cross section, it becomes so this length, this 4 lengths together times this distance A, and that is equal to A times the outer diameter, which is, let us say we take this to be D4. So, the outer diameter D out, or let us say D4 minus this part D1 and twice of that. The factor 2 comes because there are 2 surfaces. So, therefore, this is the shear stress developed, and that must be less than tau allowable. From this we can calculate the D4, or if we have already calculated, then we can check against the shearing of the socket collar. So, these are the ways in which the socket fails. The socket fails then in 3 ways. One is the tensile failure, the second is the compressive failure, that is the crushing of the socket collar against the cutter, or the shear of the socket collar because of excessive shear stress developed. So, this is how the spigot and the socket is designed. Now comes the most important thing, that is the cutter. Now let me draw the free body diagram of the cutter. Cutter this is the cutter, and this part, there are 3 parts again. This part is here. So, this is going to the socket, this part is going to the socket, and we have a compressive stress. So, here we have compressive on this side, here we have compressive stress from this side, and then again here compressive stress that side. Then what is the distributions? The distribution is a priori not known, we have to make some guess. So, in most of the design handbook, the normal distribution taken is triangular over this surface and rectangular over that surface. So, if you draw the free body diagram with that assumptions, then the free body diagram looks like the following. So, up to this part we have a triangular distribution, and also here triangular distribution. Over this part we have rectangular distribution. Now, if this is the case, then this quarter will be subjected to both shear and bending moment. So, let me draw the shear force diagram. If you draw the shear force diagram, then it looks like, so this is V x, if you measure x from this length, and V is the shear force positive over here, and this is x, then the shear force diagram will be taken to be approximately so a large negative shear force, thus this is part is negative, this is positive. So, we see the maximum shear force is here, and that is what is expected. This part is subjected to shear. So, in the case of excessive force, what may happen, the quarter may gets damaged on these two surfaces. So, we have to find out the shear stress. The shear stress is now tau will be equal to, the shear force is nothing but P by 2 over here. If you calculate, then this is P by 2, the maximum P by 2, and this is P by 2. So, therefore, P by 2 divided by the area. Area is equal to the mean width, that is, if you take W as the mean width, then W times T. So, this will be the tau, and this must be less than tau allowable or tau maximum. That is, once we have decided for T, we can find out the required value of W, that is the width of the quarter. Then this quarter is not only subjected to shear stress, but also a bending moment. Now, we have to draw the bending moment diagram. The bending moment diagram, if you draw it carefully, the bending moment diagram is so this is mx, x over here. So, the bending moment diagram is not almost look like that, of course not 0 over here. So, bending moment is maximum near the midpoint. What is the value of the bending moment here? M max. M max, okay, if P is taken to be the, instead of P here distributed, we have P by 2 acting at 1/3 distance away from this point, that is, if this length is, let us say, T2, if this is T3, and if this is T4. Now, T3 is nothing but D1, and T2 is nothing but the difference between the socket outer diameter and the D1, and similarly T4 is nothing but, T4 is equal to T2. So, in that case we can calculate the total bending moment on this sections. Now, once you calculate the total bending moment, we have left it unfinished. So, we have P by 2 acting over here. Hence, the bending moment at this point is P by 2 times T3 by 2 is equal to P by 2 times T3 by 2 and P by 2 minus P by 2 times, I am sorry, this is T3 by 2 and this distance is midway. So, this will be T3 by 4 instead. So, this is T3 by 4 and P by 2 this distance, which is equal to T3 by 2 plus 1/3 of. So, this is M max. We have calculated M max. Now, we have to calculate the bending stress. The bending stress is given by the known formula, that is sigma P is M. The maximum stress will be on the top fiber, which is equal to W by 2 My by I. I is equal to 112, then T BH cube W T cube. So, this is the value of sigma B. May be wrong here. So, this is the cross section. You see the cross section, if you take the cross section, it looks like this is T and this is W. So, we have BH cube, that is T W cube. So, this is the sigma B. Definitely, if W is quite large, then the value of sigma B is less. Nevertheless, we have to check against the failure. Now, the bending stress is tensile or compressive, depending upon which surface you are looking at. Now, this must be less than sigma allowable. When we have both bending stress and the shear stress, then we will have to calculate also the maximum principal stress. Now, in this case, this is quite complicated, but the principle is that once we have a combined kind of stress, then we will have to calculate, just like always, the sigma 1 2, which is equal to sigma x divided by 2 plus under root sigma x by 2 square divided by tau square. At each point, we will have to calculate this value of sigma 1 2, and that must be less than sigma allowable. Now, this is the failure when the material is brittle in nature, but if the material is not brittle but ductile, then we have other theories of failure. As you know, the material may fail because the shear stress may reach maximum value. So, in that case, tau max is equal to under root sigma x by 2 square plus tau square. Sometimes we use von Mises stress, then we find out equivalent normal stress, which is equal to sigma x square plus thrice tau square. So, in that case, in the former case, this value will be lesser than tau allowable, and in that case this value is lesser than sigma allowable. Now, this is how the cutter has to be designed. So, roughly we have now completed the entire design procedure. We have found out the the different modes of failure of different elements. First, the spigot may fail against tension. Now, tension failure may be in the rod or somewhere here, where the cotter is inserted within the or into the spigot. There may be the shear failure of the spigot part because of excessive contact stress developed in the cotter. So, the cotter may just or the spigot because of the excessive stress may get sheared away, and the cotter may start moving towards this direction. Then the other mode of failure is the crushing mode, that is the bearing stress developed between the spigot and the cotter may be excessive and the spigot surface may get damaged. If the force is now compressive, then there are two other types of failure, that is the collar may get crashed. The collar, when it is subjected to compressions, will develop a bearing stress because of the contact between the socket collar and the spigot collar, and this contact stress, if it is too large, then the failure may take place. The other kind of failure is the shear failure, where the spigot, because of the high bearing stress between the spigot and the socket, then the spigot collar may just get crashed. So, this part will be just sheared away. So, this is one type of failure. The socket may fail against again due to various reasons. One is the tensile failure, which happens near the critical region, which is the place where the cotter is inserted in the socket. The socket collar may fail because of the large compressive stress developed between the collar and the cotter. Also, the socket collar may get sheared away. So, these are the three types of failure present for the socket. The cotter, on the other hand, may fail because of shear as well as because of bending stress. So, when the joint is to be secured, then we will have to design such a way that the failure of the cotter should not take place. In that case, we will have to consider both the bending stress developed as well as the shear stress developed. So, this is how a cotter joint is designed. Now, in this lecture we have learned how to design a cotter joint. In the last lecture we have learned how to design a pin joint. Now, let us come further to the pin joints. Let us see. In the knuckle joint we have used, so knuckle joint was something like this. Where a pin is inserted over here. Now, in that case, the collar. So, in that case, this was subjected to tension. Now, this is the joint where two members are restrained against the tensile force. Sometimes this pin is also used when you want to fix two shafts when a twisting moment is applied. So, this is a different pin arrangement. Let me draw it. So, let us consider one shaft. And we want to connect. So, this is one shaft. And we connect it to the other shaft. So, this is another shaft. So, this is another shaft, and these two are connected by means of a pin. So, we insert a pin. Normally here for this joint we have a very little tapered pin. So, this is the pin inserted, and this shaft, let me draw that. One shaft is here and another shaft. So, this is one shaft and another shaft, let us say hollow shaft, and this is the pin. Now, what will be the failure? The failure will be against here the shear. So, if you draw the free body diagram of this part, then we have a force over here. If we apply torque, then the force developed is F is equal to T divided by D, where D being the diameter. So, in the pin, if you draw the free body diagram of this pin, there will be this force F and F here. So, the stress developed is F divided by pi by 4 d pin square. So, this is how here in this case the pin diameter is selected. This must be less than tau max or tau allowable. So, this is the case where pin is subjected to pure shear. We shall study different kinds of key arrangement where a torque twisting moment is transferred from one shaft to the other shaft in the next class, but this is also done by means of pin arrangement as I have discussed over here. So, in the next class we are going to study how to join two shafts when a twisting moment is transferred from one shaft to the other shaft. So, this is done by means of keys and splines. So, the next lecture will be devoted on keys and splines. In this lecture we conclude with this pin joints and quarter joints. So, we have learnt how to design a quarter joint and how to design a knuckle joint in these two lectures. We have discussed in details how to join different elements. So, from now onwards we are not going to make some detailed analysis, leaving something to the students, something to you to fill up the blanks, and we are going to just give the outlines of the design procedures. So, this is the end of today's lecture. Thank you very much. Dear student, let us begin lectures on machine design part 1. This is lecture number 15 and the topic is design of keys and splines. Now, in last two lectures we have known how to design common types of fasteners, namely the knuckle joints or the quarter joints. Now, in those joints mainly the purpose was to transmit tensile or compressive force from one member to the other. But there are cases and many cases in a machine where we have to transmit torque from one shaft to another shaft which are which have the center line the same. So, these are very common things, and we have to design a fasteners such that the torque can be transmitted from one member to the other quite efficiently. So, we are now going to start discussions on keys and splines. So, these are the again one kinds of fasteners, that is the non-permanent type of joints where the torque can be transmitted from one shaft to the other shaft. So, these are very important things, and the design is quite difficult. Exact design, exact analysis is quite difficult, but we are going to design give some guidelines of the design. Now, let us first come to the basic types of keys. So, we are going to divide the lectures into two parts. One is the design of keys and another is design of splines. In some books you will find splines are taken to be one kind of keys, but for our discussions we are keeping them separate. So, let us see what are the different types of keys. Now, the purpose of the keys, as I said, is to transmit torque from one shaft to the other shaft. That is, if we have a shaft over here, then this is one shaft. Let us think of another shaft which is concentric. So, these are two shafts where the torque has to be transmitted from this shaft, from the inner shaft to the outer shaft. The means of doing so is by using the keys. Now, the keys are a small piece of some material which is the same as that of the shaft material, where these are normally rectangular in cross sections. So, here we see that what we do, we cut two slots in both the shafts and then insert one small piece which is known as the keys. So, here we have cut one keyway and this is key. If you draw it in further details, then what you see is that, let us draw the outer shaft. The outer shaft, here we can get, so this is that part of the outer shaft, where this key slot is cut. The inner shaft, again we have another, this is the inner shaft where another slot is cut. Normally these two heights are equal. If the total height is h, then this is h by 2, and so this is the slot for key, and we insert a key over here. Now, there is a small clearance, a tolerance. This is because of the machine fitting. So, this is a tolerance, a very small tolerance, that also depends on the keys, the dimensions of the keys, but there is some tolerance. And so, this is how the key looks like in a key slot. Now, this part, which is the corner of the keys, this part, this is now little chamfered.